Let's look at the fundamental theorem for line integrals. Here's a path. We label it C1. It starts at the origin, it ends at the point 5,5, and it's designated by this red path here. So it's two line segments basically. And what we're asked to do is to compute the line integral of the vector field about C1. And our vector field F, first component y squared, second component 2xy. And of course, the labeling we use for the first coordinate is m, and for the second coordinate is n. Now, when we do this line integral, in general, we would parameterize the path and then apply the definition of line integral. But what we want to do here is see if we can actually use the fundamental theorem for line integrals. So we're going to check to see if our given vector field is conservative. So we take the y partial of the first coordinate and we get 2y. And we take the x partial of the second coordinate and also get 2y. So by definition, we have a conservative vector field. Now, of course, my technique for computing the potential function is rather abbreviated, but it gets to the result quickly without a lot of formalism. And normally I really like the formalism, but this is the quickest way to get to the potential function. Just go ahead and integrate in both variables. That is, we integrate m with respect to x and we integrate n with respect to y. And upon doing that, we get xy squared plus some constant that could be a function of y. And then in the second integral, we get the same term, xy squared plus a constant that could be a function of x. So again, less formalism, but we still get what we need. So by comparing these two equations, we see that our potential function has to be xy squared plus an arbitrary constant. Now, what I've written here is use the fundamental theorem. The fundamental theorem is just like what we see in Calculus 1 and Calculus 2, but it's the fundamental theorem for line integrals. So similarly to the fundamental theorem in Cal 1 and Cal 2, we basically just evaluate the antiderivative at the endpoints. So we have our line integral about C1 f dot dr, which is equivalently y squared dx plus 2xy dy about C1. But now, of course, this is replaced, the antiderivative is just the potential function. That is, when we do this computation, what we have is the gradient of the potential function is f. And that's what makes this work. It's like anti-differentiating the derivative, and we're left with the function. And so now we simply evaluate the antiderivative at the endpoints. 5, 5 will give us 5 times 5 squared, and of course the 0, 0 just zeroes out. So we get an answer of 125, which is a big time savings. So conservative vector fields in differential geometry, calculus, physics, very important. And as you take more engineering and physics, you'll see more applications of conservative vector fields. Now, I wanted to give you another example of this. For the next curve, we call this C3. It's actually polygonal, just like this one, but it's closed. So it connects all 4 of these points via line segments. But the fundamental theorem says if we have a conservative vector field, then the line integral about any closed path is necessarily 0. So that's another big time saver. Now, one thing that's very important is that the first partials must be continuous in the region bounded by this curve, and we see we have that. Now, of course, we have to be careful when we're analyzing vector functions that they actually meet the hypotheses of the fundamental theorem, but we have no issue here. And of course, we have a piecewise smooth curve, so all the hypotheses are satisfied. And so now we simply write this out just to be clear as to what we're doing, but the answer is 0. And so what we want to observe here is that it is always worth it to determine whether or not you have a conservative vector field, because the line integral computations will be much simplified. And we are done.